Hello, my name is Jihyuk, and today I'm here to present the research that's been done in collaboration by Université de Sherbrooke and INSA Lyon, titled Numerical Simulation of the Heat Transfer in a Refrigerated Trailer Equipped with Eutectic Plates for Frozen Food Delivery. Currently, approximately 2% of the total greenhouse gas emissions in developed countries are produced due to food transport, including motive power and refrigeration. And for medium to large sized truck trailers, uh, self-contained diesel engines are primarily used to refrigerate and maintain the temperature inside the truck trailer. Eutectic systems are a system that composes of beams, plates, or tubes filled with a phase of change materials that is used to maintain the temperature inside the trailer, which shows a promising solution, which seems to be a promising solution to improve transport efficiency and quality, as well as reducing reliance on fossil fuel consumption. However, for such system, a major concern is during the door opening period, especially in humid climates. Majority of heat infiltration that occurs for such system are during the door opening period, and during the door opening period, condensation and formation of ice and frost along the plates can occur, which interferes with the heat transfer between the plates and the surrounding air. Previously, Carger et al. Developed a CFD model of a truck trailer equipped with eutectic plates and validated against the experimental and numerical data of Lafayette-Dumichaux et al., which is going to primarily be used for this research. The main objective of this research was to extend the former works of Carger et al. Using the same validated CFD model to simulate the refrigeration system with eutectic plates and analyze their trailer temperature, cargo temperature, and infiltration heat load for two different operating modes and two different configurations. For the numerical model, INSA CFX version 19 was used, which solved for 2D unsteady Reynolds average Navier Stokes equation, as well as K omega SSD turbines model. For the transient simulation, instantaneous door opening was assumed at time is equal to 0 seconds and the fans were turned off. For the initial parameter inside the trailer, for the transient simulation, results of the steady state simulations were taken. For the steady state simulation, the doors were closed and the fans were turned on until the conversions was reached. So the two different configurations were primarily investigated for this research. Configuration A on the top, where the plates are located on the back of the trailer in parallel, and configuration B, where the plates are located on the roof of the trailer in series. Two different fan operating modes were also investigated. Blowing mode, where the air is blown out from the plate region into the trailer, and suction mode, where the air inside the trailer is sucked into the plates. For the fans were modeled by adding a source term in the momentum equation and with a velocity of 8.4 meters per second to match the existing fans. Plates were kept at a constant temperature of 244 Kelvin. The walls were heat conducting, and the temperature outside of the trailer was at 293 Kelvin with zero velocity. So this is the mesh parameter that has been used. A minimum of 10 prismatic layers were added close to all walls and plates with the gross ratio of 1.1, and the thickness of the first prismatic layer was approximately 1.25 times 10 to the power negative 5 meters, which ensured Y plus value to be less than 1 for the K omega SSD model. And approximately 960,000 nodes provided great independent results for both configuration A and B respectively. Though the 2D and the 3D model were first validated against the experimental and numerical model of Lafayette-Dumichaux et al. The one you see here is the infiltration rate profile of the 2D and 3D configuration that were tested. So the 2D model shows generally a good agreement with the numerical and experimental values that were obtained by Lafayette-Dumichaux et al. The 3D model showed a slight negative infiltration that occurs between time equal to 15 to 22 seconds, which is coincides with the time when the large eddy crosses across the door, which cannot be seen by the 2D models or the experimental and numerical data of Purdue et al., as it takes a value from the door center line in average for the infiltration rate. This is the transient results. That's simulation for the configuration B blowing mode. As the door opens, you see an initial infiltration that occurs on the top and the bottom of the trailer. Then that infiltration gets limited due to the circulation zone inside the trailer, as well as exiting cold high velocity air. Then the further infiltration occurs as the circulation zones inside the trailer diminishes over time. And you see the infiltration reaches the back of the trailer, and the air inside the trailer is mostly filled by the atmospheric air by this point. So the same simulation were performed for each configuration and each operating modes for the fans. For all the configurations, generally at 2.5 seconds, you see an initial infiltration of the atmospheric air through the top or the bottom of the trailer, depending on the rotation of the pre-existing flow inside the trailer. Then between times equal to 2.5 seconds to 10 seconds, you see the infiltration rate gets limited by the existence of the circulation zones inside the trailer that's been developed by the pre-existing flow that's inside the trailer, as well as initially infiltrated atmospheric air at times equal to 2.5 seconds, which forms a circulation zone as well. And the cold high velocity air that's exiting out of the trailer also limits such infiltration. But then over time, between times equal to approximately 10 seconds to 20 seconds, you see further infiltration that occurs as the circulation zones that were limiting the infiltration gets progressively diminishes over time. One noticeable thing about this figure is that for configuration B, it performs significantly better than that of configuration A, as you see from the temperature profile. This is due to the fact that the circulation zones inside the trailer better limits the infiltration rate, as well as the presence of the cold air in the located around the plates that is close to the doorway. As you see in times equal to 10 seconds, you see that the such cold high air on or surrounding the plates located near the doorway prevents further infiltration and delays it for a longer time than that of the configuration A. This is the infiltration rate profile for all of the configuration that were described and the operating mode that were described in the previous slide. You see an initial peak infiltration rate that occurs as the initial atmospheric air infiltrates into the trailer. Then it sharply decreases as the exiting cold high velocity air and the circulation zones prevents further infiltration. Then you see a steady infiltration that occurs as the infiltration slowly advances towards the back of the trailer, as the circulation zones that are limiting the infiltration diminishes over time. From 30 times equal to 35 seconds to 40 seconds, you see a similar infiltration rate value for all of the configuration and all of the operating modes, as the trailer is now mostly filled with the atmospheric air. Therefore, the infiltration is solely caused by the presence of the plates. For the configuration B, it takes 91% to 88.5% longer to reach the renewal time, which is defined as time it takes for the initial volume, internal volume of the air inside the trailer to be renewed by the atmospheric air, compared to configuration A for blowing and suction mode respectively. So the same transient simulations were repeated with the presence of cargo, which is frozen meat. For the transient simulation with cargo, configuration B blowing mode was chosen for its best performance in terms of renewal time without cargo. For configuration A, suction mode was chosen for the comparison to be consistent with the direction of the rotation of the flow inside the trailer before the door opening, both of them being counterclockwise flow inside the trailer. The one noticeable thing about the steady state result is that for the configuration B, the area average velocity is 31.7% lower than that of configuration A due to the blockage of the flow that occurs by the presence of the cargo at the back of the trailer. Whereas for configuration A, that cannot be seen as the plates, as the air from the plates are directly fed into the gap between the bottom of the trailer and the cargo. So this is the transient simulation of the configuration B with blowing mode with the presence of the cargo. As the door opens, you see an exiting and mixing of high cold velocity air, and you see infiltration through the top of the trailer, which is being limited by the exiting cold air on top of the cargo. For configuration B, due to the recirculation zones at the back of the trailer, due to the flow that's been deflected and blocked by the presence of the cargo, the temperature change decreases slower at a later time than that of the configuration A. These are the transient results with cargo for configuration A on top and configuration B on the bottom at times equal to 2.5 seconds, 5 seconds, 10 seconds, and 20 seconds. For most of them, you see a similar results. At 2.5 seconds, you see a strong exit of the cold high velocity air, as well as mixing that occurs with the atmospheric air. And then from times equal to 5 to 20 seconds, you see an infiltration that occurs along the top of the trailer with the exiting of the cold air on top of the cargo. Because of this limited infiltration that occurs due to the exiting cold air on top of the cargo, the renewal time for configuration A increased by 96.2%. However, it decreased by 8.3% for configuration B, as the presence of the circulation zones cannot be seen by the car due to the presence of the cargo. One noticeable thing about this is also that because the velocity of the air inside the trailer before the door opening is higher than by 31.7% for configuration A than configuration B, initially the air infiltrates at a more defined rate than that of the configuration B. But then, due to the strong mixing that occurs by the higher velocity, the more pronounced infiltration is delayed for configuration A than configuration B. Due to this reason, the temperature inside the trailer increases at a higher rate for configuration B, and when the atmospheric air begins to mix contact with the cargo. Therefore, after 40 seconds of the simulation, configuration A showed 1 to 2 degrees lower temperature for the cargo than the configuration B. This is defined better on the temperature profile, where it's separated into 3 different zones. In zone 1, between times equal to 0 to 5 seconds, the initial temperature inside the trailer for configuration A is higher than that of configuration B, as the higher velocity air exiting out of the trailer drags in more atmospheric air than that of the configuration B. However, between times equal to 5 to times equal to 25 seconds in zone 2, the stronger mixing that occurs by the higher velocity of cold air that has exited out of the door for configuration A delays more pronounced infiltration for configuration A. Therefore, the temperature increase is higher for the configuration B than that of configuration A. So in this region, you see a higher temperature for configuration B than configuration A. And in zones 3, between times equal to 30 seconds to 40 seconds, the recirculation zones that were present for the steady state case for the configuration B decreases the further temperature change for configuration B. Thus, the temperature inside the trailer for configuration B being lower than that of configuration A. However, during the time when the atmospheric air or the mixed air begins to make contact with the cargo, which is from the time zone 2, you see that the configuration B has higher temperature than that of configuration A, which led to the cargo temperature for configuration B being higher than that of configuration A, as seen previously. So in conclusion, without the cargo, the configuration with the plates placed in series on the roof of the trailer noticeably improved the performance in terms of the renewal time and the infiltration rate due to the presence of the circulation zones and the cold air that surrounds the plates that is located near the top of the doorway where the infiltration occurs. However, introduction of cargo into the simulation eliminated the effects of the circulation zones that acts to prevent the infiltration of the atmospheric air, and therefore the configuration with the plates placed on the roof of the trailer with cargo, due to the lower initial velocity that has occurred of the flow inside the trailer due to the recirculation that has been formed by the blockage of the flow by the cargo, the atmospheric air was able to infiltrate and increase the temperature of the trailer earlier, resulting in a higher maximum temperature observed for the cargo. However, as the number of cargo boxes will progressively decrease during the entire delivery cycle, it is plausible to assume that the configuration with the plates placed on the roof of the trailer could improve the performance over time, and as the presence of the circulation zone that we're seeing without the cargo will progressively emerge as the number of cargo boxes will decrease. The influence of the cargo parameters such as cargo locations, dimensions, arrangement should also be investigated, as we've seen that these parameters have significant impact on the pre-existing flow before the door opening period, which has an impact during the door opening period as well. And further development should include a multi-phase model to account for the humidity of air, phase change of eutectic mixture, and formation of frost and ice along the plates. And these were the references that were used for the presentation. And thank you for listening to my presentation on the research. And thank for the universities and the industrial partners for this research to occur. Thank you.